All right, so can you guys all see the PowerPoint with me here?
Yeah.
All right,
Yeah.
let's start. So this chapter is all about chemistry and measurements. So we're going to be talking about units of measurement for various things like length, mass, time, basic things. And then we'll also review how to convert between different units and how significant figures apply and how significant figures apply with scientific notation. So it's a little dry, but bear with me. So your chapter starts, they use nursing or doctors as an example of measurements, right? So like when you go see a doctor, the nurse takes your blood pressure, they measure your weight, different things like that. And so all of those measurements have their own units and place values and things of that sort. So the math skills we're going to talk about are identifying place values, using positive and negative numbers in those calculations, calculating percentages, and writing numbers in scientific notation. So units of measurement, there's a unique unit for everything that you measure, right? And so here's an example of a couple taking a walk and, what time of day is it? We measure time in seconds, minutes, hours, right? How tall are the people? We can measure height in meters, in feet, in inches. Those would be units of length, right? How much did each person weigh, right? You can measure their weight in kilograms or pounds. Those are different units for weight or mass. How far are they walking, right? We have units of distance. So you can measure that in kilometers, miles, meters. So, and how warm is it outside, right? Temperature, we measure in degrees Celsius or degrees Fahrenheit or Kelvin. So different units for the different things that you measure. So there are 3 systems of measurement units. There's the English system, which you guys are familiar with, right? Pounds, ounces, fluid ounces. And then there's the metric system, which we use in the sciences. Now the metric system uses grams, meters, liters, okay? And there's also the international system of units. Now the international system of units is based on the metric system, but they specify what the standard unit is. So here's a chart. And so you've got the metric and the international, abbreviated SI. And so for the metric system, the standard unit of length is the meter, volume is the liter, mass is the gram, temperature is degrees Celsius, and time is in seconds. For the international standards, they use cubic meter for the standard unit of volume, and they use kilogram for the standard unit of mass, and they use Kelvin as the standard unit of temperature. So these 3 are different between SI and metric. Now, keep in mind, cubic meter, kilogram, and degrees Kelvin are interchangeable with the metric system, but these are just the standard unit for the SI. Technicality, probably never going to ask you about that. Okay, so let's take a look at the meter and centimeter, millimeter, or kilometer. So a meter is familiar to you guys as maybe a yard, right? In the English system, we use yards, and we have a yardstick. The metric system, you have the meter stick. They're almost the same length. They're slightly different. So 1 meter is 1.09 yards. It's slightly longer. And so 1 meter has 39.4 inches in it, whereas a yard has exactly 36. And so the conversion that you guys will probably be using here is 2.54 centimeters is equivalent to 1 inch, right? So if you hold up a meter stick and a yardstick, you can see that the 1 inch mark is right at 2.54. So that's how you can convert between the English system and the metric system for distance.
Are you going to have us, or not you, but is the class going to require for us to memorize the conversion factors?
Absolutely not.
Okay.
I will give you conversion factors. I don't think memorizing this is useful whatsoever. I mean, you could Google this, right? If you ever need to do the conversion, you can say, hey, Siri, like what's 25 inches in centimeters, and they'll just spit it out. Like there's no point in memorizing this. But understanding how to use it, yes. So I will have you convert between one type of unit to another. But like on the quiz, it's going to be open note. And then if it's an exam, I will give you these conversions.
Oh, yeah.
Okay. Liter and milliliter. So the liter is the standard unit of volume for the metric system. Okay. And the conversion between metric and English is like this. So 1 quart or 4 cups is equivalent to 946 milliliters. It's almost 1 liter per quart, but not quite, right? So a lot of people abbreviate a gallon is about 4 liters. That's like a pretty rough estimate, which is useful if you ever travel international and you're buying gasoline at a gas station, because in America, it's always price per gallon. But like in Europe, it's price per liter. So if you're trying to figure out whether it's expensive or cheap, just think like 4 liters per gallon. And one of the laboratory pieces of equipment that you use to measure volume is known as a graduated cylinder. It's basically just a tube that has a bunch of marks, right? And so you pour your liquid in there and it tells you exactly how many milliliters of liquid are in the tube. Okay, for mass, we use the gram or the kilogram, right? Now, the conversion you guys are probably going to use the most is this one. So in the English system, we use pounds. The metric system uses kilograms. And so it's about 2.20 pounds per kilo. So that's the English to metric conversion. And the device that you use to measure mass in a laboratory setting is usually a scale. And so here's just a picture of somebody measuring the mass of a nickel. And you can see it's 5.01 grams. All right, temperature, we use thermometers.
That's another question.
Yeah, what's up?
As far as the grams and the weight, is that pretty standard? Like, does that ever change at all? I mean, as far as like that nickel, for example, is it always going to be that?
You mean this conversion? Or
Yes.
yeah,
Correct.
this is standard. Yeah, 2.2 pounds is 1 kilogram by definition. This is how
So
you,
if I have a kilogram of, like, let's say candy, it's going to be the same as that. As long as it's 1 kilogram.
yeah, 1 kilogram of any material is exactly 2.2 pounds of that material.
Okay, thank you.
Yeah, so if you weigh yourself and you're like 150 pounds, and you want to know how much that is in kilos, you would just divide by 2.2. That's how you go between 2 different units. So temperature can be measured in 3 ways. We have degrees Fahrenheit, degrees Celsius, and then Kelvin. And those are just 3 different scales. So your book doesn't have a good reference image of this, but Kelvin is based on the concept of absolute zero. You guys may never have thought about this before, but what is temperature? What are you measuring with temperature? So molecules actually vibrate. And the faster they vibrate, the hotter it is. So when you're measuring temperature, you're essentially measuring the vibrational rate of all the molecules. Okay. So as you go down in temperature, molecules vibrate less and less. There is an absolute zero, right? The coldest that cold can get, and that is where all molecular vibration stops. All molecular movement ceases. It's more of a theoretical concept. We can't reach absolute zero. The closest we've gotten is about 4 degrees Kelvin, which is colder than space. And that's about as cold as we can get. It's not absolute zero. So theoretically, molecules will stop moving at 0 Kelvin, but we've never been able to obtain 0 Kelvin. So the Kelvin scale starts at 0. So all temperatures are positive. Whereas Fahrenheit and Celsius, 0 is sort of arbitrary. And so you can have a negative temperature. And so Kelvin temperature is always positive by definition. So this is wrong here. This is supposed to be degrees Celsius. So water freezes at 32 degrees Fahrenheit or 0 degrees Celsius. And so those are the definitions for Fahrenheit and Celsius where they start. Okay, time. Time is measured in seconds. And so, or minutes or hours, right? And so the standard SI unit for time is the second. So pretty much everyone's familiar with that. Okay, study check. What is the SI unit for each of the following? What's the SI unit for volume?
Oh, okay, I see what you're
Cubic
saying.
meter.
Yeah,
Oops. What's the SI unit for mass?
Kilograms.
Kilogram.
Kilograms, good. And length
meters,
and temperature.
Kelvin.
There you go. Pretty easy.
I didn't know what you were talking about at first. Okay, this makes sense.
Yeah, SI unit. So the international standard for units. This might seem silly, like why are we having you guys memorize this? It makes more sense in international collaborations. So like if NASA is collaborating with, you know, an engineering firm in some European country and they're doing measurements for something they're going to do on the space station, you want to make sure everyone's doing everything in the same unit. And so as long as you use SI units, it's going to be all the same, right? So, you know, in America, we always use the English system and we don't have to worry about it. But if you collaborate with people in different areas, you know, having a standard unit that's accepted, make sure that everyone's on the same page.
In medicine too, they do it a lot, right?
Yeah, in medicine, yeah, right. Like if somebody says, "Oh, go give the patient, you know, 150 milligrams of whatever drug," it's 150 milligrams because everyone uses milligrams, right? Okay, so section 2.2, we're going to talk about measuring numbers and significant figures. So whenever you're measuring something, you're always going to have a known number and an unknown number. Now this seems silly, but if you're measuring this stick right here, how long is the stick?
5 centimeters. Oh, the stick is 4.5.
4.5, right? So you can say it's
Estimated.
you could say it's 4.5, right? The 4 is known because there's a mark at the 4. But why do we say 0.5?
Because it's halfway.
It's about half. Do we know it's exactly halfway? There's
We're
no markings here.
guesstimating.
No, but
So
it's an
yeah, we
estimate.
estimate. So this is a guess. We're guessing it's about halfway. Now, if there was a mark right here, then you'd know it was exact. But so for any tool that you have for measuring things, there's always going to be a guess. The last digit is a guess because you're going to be in between the markings, essentially. So measured numbers are measures that you obtain from actually measuring something, right? So here, the length of this stick is a measured number. You also have counted numbers. So like if you had a, I don't know, a fruit bowl with apples and there's 6 apples in there, that's an exact number because you counted it. There's exactly 6. If you measure something, it's a measured number. And so anytime you have a measured number, the last digit is a guess. Anytime you count something, it's an exact number. Okay. So here is a further example of measured numbers. So this first one is 4.5 because you're halfway between the 2 marks. Now, if your meter stick had smaller ticks there, now you can say it's exactly 4.55 because it's somewhere in between the 4.5 and the 4.6 mark, right? Or if it was here, you would say, oh, it's 3, right? You could say 3.0 because you're guessing that it's exactly 3. So your last digit is always the guess. So significant figures refers to the number of digits that are important, okay? And so here you had 2 significant figures, here you had 3 significant figures, and here you had 2 significant figures, okay? Now, in the middle example, the reason why we have 3 significant figures is because we have more tick marks, so we can be more accurate with the measurement. Okay, so saying 4.55 is more accurate than saying just 4.5. Okay, so the number of digits in an answer correlates to how accurate your measurement is. And so it's important to keep track of how many digits you have in an answer. Okay. And so there's some rules for significant figures. They're kind of tedious, so bear with me here. So there are rules for including zeros in your significant figures. Okay, let's go through some examples and then hopefully these rules will be self-evident. So a number is a significant figure if it's not a zero. Okay, so in these first 2 examples, you have 4.5 or 122.35, right? These are actual integers, and so they count, right? So it's 2 sig figs here, 5 significant figures here. Now, if you have a 0 between actual numbers, that 0 counts as a sig fig. So 205 has 3 sig figs. 5.008 would have 4 sig figs because the zeros are sandwiched between whole numbers. Now, if you have a 0 at the end of a decimal, it's significant, right? So 50 with a decimal is 2 sig figs. 25.0 is 3 sig figs. 16.00 is 4 sig figs. So if there's a decimal, the zeros are important.
Okay, but only if the 0 is before the decimal, because like what if
Even
the
if it's
5
after.
0?
If
Oh,
this
okay.
is actually if it's after at the end of a decimal.
Oh, right, 16 point, okay.
Yeah. It's important if the number is written in scientific notation and there's a 0 in the coefficient. So like 5.70 times 10 to the negative 3 has 3 sig figs. Okay. So anything written in scientific notation, if there's a 0 in there, it's significant. Now, the one where the 0 is not significant is when it's at the beginning of a number, if it precedes the first whole number. So 0.0004 has 1 significant figure, just the 4, because everything before the 4 is all zeros, so we don't care. 0.075 would have 2 sig figs, the 7 and the 5, because the zeros out front don't matter. Now, if the zeros are at the end and there's no decimal, they're also not significant. So like 850,000 only has 2 sig figs. 1,250,000 only has 3 sig figs. Okay. Now, if this was a decimal at the end, those would count. But if there's no decimal, then they don't count. Okay. So I'm not going to grill you guys about these technicalities, but these are the rules for sig figs. Okay. So a lot of times when you have a huge number like this with a bunch of zeros, if they're not significant, when you write it in scientific notation, it makes more sense, right? So let's take a look at 850,000. If we were to write this in scientific notation, what would it be?
8.5 times 10 to the 4th power, 5th power. Yep.
And so how many sig figs do we have?
2.
2 sig figs. This also has 2 sig figs, right? Okay. So it makes more sense when they're written in scientific notation because you can easily see the significant figures. So here are some more examples of converting large numbers into numbers written in scientific notation. So 400,000 would just be 4 times 10 to the 5th. And so you can see it's just 1 sig fig. 850,000, 8.5, right? 0.0004, just 4 times 10 to the negative 4, right? 0.000046, 4.6 times 10 to the negative 6. So when they're written in scientific notation, it's a lot easier to see how many sig figs there are, as opposed to when they're written out like this. Okay, so identify how many sig figs in each of these, basically. And then write it in scientific notation. So the first one here, how many significant figures do we have?
5.
6.
Sorry.
No, it's 4.
3?
Do the zeros out front count towards the sig
No.
figs? They do not,
No.
No.
right?
It's 4.
It should be 4, 2, 6, 5, 0. So how do we write this in scientific notation? And how many places did we move the decimal? 1, 2, 3. And that should be 4 sig figs. All right, what about the second one? 43.026.
5.
Should be 5 sig figs. How do we write that in scientific notation?
I think that's correct.
All right, and what about the last one?
4.
4 sig figs, right? And how do we write this in scientific notation?
1.044 times 10 to the 5th power.
It should be the 6th power,
6th power, 6th power.
6, yeah.
and that is 4 sig figs. And those are the answers. So, okay. So we just talked about measured numbers, right? So when you get a number from making a measurement, you have to worry about sig figs. The next type of numbers are exact numbers. Now, exact numbers have an unlimited number of significant figures, right? Every digit is significant in an exact number. So the way you get exact numbers are by counting something. So like if you counted 8 cookies, there's exactly 8, right? You don't have to worry about sig figs. Definitions are exact numbers. So like a dozen is 12, right? That's like exact. 1 quart equals 4 cups. Those are exact, right? 1 kilogram is 1,000 grams. That's an exact conversion. So these, you don't have to worry about sig figs. So here's just some examples of exact numbers, right? Counted numbers, metric conversions, or US conversions. These are exact by definition. So you don't have to worry about sig figs. All right, so identify each of the numbers below as exact or measured and the number of sig figs. So if we say there's 3 coins, is that a measured or exact number?
Exact number.
That's exact because somebody counted it. The diameter of a circle,
Measured.
that would have to be measured, right? And how many sig figs?
4.
3?
It's measured and it's 7.902.
So it's
So-
4.
4 sig figs. Right, and then the last one, 60 minutes is equal to 1 hour.
Exact.
That's exact. That's a conversion. Good. And there's the answers. Okay, so your book goes on a brief little stint about how to use a calculator when you're dealing with measurements and rounding, right? So when you use a calculator and you have some decimal, it's going to give you like 100 digits or however many you can see on your calculator. It doesn't mean those are all significant, right? So you have to round in chemistry, right? You plug something into your calculator and it tells you like, oh, 4.796359, you know, and it keeps going forever. You always want to round it to the number of significant figures relevant to the problem. Okay. And so whenever you're rounding, 4 gets rounded down, 5 or more gets rounded up, right? And so let's say this was the number you got on your calculator in this column. And then let's say we're looking at 3 significant figures or 2 significant figures, right? How would you round each of these? So 8.4234. If you want to round it to 3 significant figures, you would look at the 3rd position, which is the 2, right? And you look to the right.
8.4.
3 is lower, so it's going to round down. So it's just 8.42. Now, if you're rounding to 2 significant figures, you look at the second number, 8.4, and then to the right of that to 2. So you just round it down to 8.4. 14.780 rounded to 3 sig figs. So you're going to be rounding the 3rd position. So you look to the right, 8 is higher than 5, so you round up to 4.8.
Yes.
What if you want to round this to 2 sig figs?
15.
You look at the 2nd position, and then you look to the right of it. 7 is higher than 5, so you round up. So this is actually just 15 rounded to 2 sig figs. 3,256, right? If you want to round it to 3 sig figs,
It's 3003.
so you want to round the 3rd number here. So you look to the
Yes,
right.
up.
6 is higher, so you'd round it to 3,260. Right? So there's 4 numbers here, but remember, a 0, if there's no decimal and it's at the end, is not a significant figure. So 3,260 is 3 sig figs. What about 2 sig figs? You want to round the 2nd place. So you look to the right of it. It's a 5, so we round that up. So this becomes 3,300. And this is 2 sig figs because those zeros don't count, because they're at the end. Just have questions on that?
No, that makes sense. Thank you.
Okay, so here's an example. Let's say we have 45,628. What is this rounded to 3 sig figs? You guys tell me.
4,000.
560.
Yeah.
45,
6.
4,560, wouldn't it be?
So if you're rounding it to 3 sig figs,
46.
4560.
Is it 45,600?
45,600.
Why? Okay.
600.
So this is 45,000, right?
It's still
So when
3
you're rounding
digits
it, it's
and
still
those are
gotta be
significant.
45,000,
Okay, okay,
but
okay.
you only worry about the first 3 numbers, right?
Yeah.
So the zeros at the end are not significant, but they
Okay.
still have to be there, right? If you didn't have those zeros, this would just be 450. So these are basically placeholders. So you got to have the placeholder there, even though they're not significant. Does that make sense?
Professor, so if it would have said like 4,000, like 650 or 700, would that increase it to 46?
Yeah, so here, let's round this to 2 significant figures.
4.
46,000.
Okay, thank you. That makes sense.
Yeah, so your question was perfect, right? So if you're rounding to 2 sig figs, you rounded the 2nd number, and the rest of them are just placeholders. They still have to
Okay.
be there, but
So
Okay,
you
thank you.
you have to put the zeros.
Yeah,
you do have to put the zeros.
Because
But
if not,
they're
it changes
not,
the value.
yeah, if they're not there, it changes the amount drastically.
Okay,
Yeah.
thank you.
So significant figures are a measure of accuracy. Remember when we were talking about the ruler? Right? If there's more ticks, you need more digits to be accurate. But you know, this is less accurate than this, but you have to have the zeros there, so it's still 46,000. Otherwise, the number would be like way off. So this is technically a less accurate measurement.
That was just a warm up.
Okay. All right, write the correct value when 3.1457 is rounded to each of the following. 3 sig figs.
3.15.
0, 0.
3.1.
3.15, yes. Yes.
So the reason why we don't need zeros out here is because there's a decimal. Okay. All right, and those were the answers. Good. Okay. So whenever you're multiplying or dividing measured numbers, you're going to be dealing with numbers that have sig figs, right? Now, you're always limited to the number with the fewest significant figures, okay? So here, let's say you're multiplying 24.66 centimeters by 0.35 centimeters. Which one has fewer sig figs?
0.35.
Right. And so your final answer can only have 2 sig figs. Okay. So when you do this on a calculator, it's going to spit out 8.631. But that's not correct because you only want 2 sig figs. So you got to round it 8.6. Right?
Around
So your calculator will always give you a bunch of digits, always round it to the lowest number of sig figs. So here's another example. You have 21.5 centimeters times 0.30 centimeters divided by 1.88. What's your limiting sig figs?
2 because of the 0.3.
Right, 2 sig figs is limiting. So when you do this on a calculator, it's going to spit out 3.4308511063. We don't care about all that. We want to round it to 2 sig figs, so 3.4. So the take home message is whenever you're doing an equation, make sure your final answer has the same number of sig figs as whatever your lowest sig fig number was. So sometimes you have to add zeros to make sure the sig figs match up. This is like a weird technicality. So let's say you have 6.0 divided by 2.00. Okay. So what's our lowest number of sig figs?
1.
6.0 actually has 2 sig figs because there's a decimal.
Oh, right. Sorry. Mhm.
No, it's okay. So this is basically a more accurate measurement. This is exactly 6, right? But because you have 2 sig figs, your final answer needs to have 2 sig figs. So if you do 6.0 divided by 2.00, the calculator is going to spit out 3. But you need 2 sig figs, so it's got to be 3.0. It's a way to show accuracy of your measurements. It's exactly 3. Okay, so what would this be with the correct number of sig figs? This is going to be like an exam type question. So I don't have a calculator out. Let me pull it up. So your calculator is going to spit out 8.52
It's
centimeters.
gonna be 8.520 because there's 4 significant figures.
We want the lowest number to dictate.
Would that be 8.5?
It would be 8.5.
Because the true gets dropped. Okay,
This only has 2 sig figs, so your final answer can only have 2 sig figs.
It's making sense.
I know this is tedious. It's really technical stuff. Don't stress about it too much. So once again, you do it in a calculator, it's going to spit out 8.52, but we only need 2 sig figs, so you round it to 8.5. Okay. The same thing happens with addition and subtraction, right? You always want to end up with the lowest number of sig figs. So here, if you were adding up 2.012, 69.09, 3.0, right? You add all those up on the calculator, it's going to spit out 66.102. But the limiting one was the 3.0. Okay. Now, instead of going with the total number of sig figs, you go with the fewest number of decimal places for adding and subtracting. So
since the 2 doesn't get rounded up and the 0 is nothing, they drop.
yeah, so the 3.0 is the 10th place, like 1 digit past the decimal. So you want to make sure your answer is 1 digit past the decimal. So if you had 65.09 minus 3.0, it's 62.09.
Around
But our lowest one is the 10th place. So your answer has to be 1 past the decimal. Let's do a practice. So if you were to add these up, you would get 104.409.
So it'd be 104.4.
104.4
Right, because it's
because the
one.
9 goes up, but the 0 is nothing.
Yeah. So you want to round it to the 1 place past the decimal. Right. Okay. So the next section, we're going to be talking about prefixes and equalities. So a prefix is the word that goes in front of your measurement to denote the scale, right? So you guys are probably familiar with the difference between a millimeter, a centimeter, and a meter, right? So the milli and the centi are prefixes that give you scale, right? You know, a millimeter is tiny, a centimeter is kind of small, and a meter is, reasonably large. So whenever measurements are given, it's important to put those prefixes so people know what you're talking about, right? So the book example is you have an ophthalmologist measuring the diameter of your retina, and that's usually given in centimeters because that's the relevant scale. And so here is a table showing large prefixes. So thankfully, because of computer technology, everybody's familiar with these nowadays, right? So back in the day, computers measured things in bytes because they were really slow. And then you had kilobytes and then megabytes. And now you guys have flash drives with gigabytes of storage or a terabyte of storage, right? So everybody's familiar with kilo, mega, giga, and tera. What they mean is a kilo is 1,000 of something, mega is 1,000,000, giga is 1,000,000,000, and tera is 1,000,000,000,000, or 10 to the 12th, 10 to the 9th, 10 to the 6th, 10 to the 3rd. So that's what those prefixes mean. Now there's also prefixes for small scale, right? And so a deci is a 10th of something. A centi is 100th. Milli is 1,000th. A micro is a millionth. Nano is a billionth. And a pico is a trillionth of something. So that's the small scale. Okay. And so if you were to write kilo in front of a measurement, that just means 1,000 of it, right? So a kilometer is 1,000 meters. Kiloliter is 1,000 liters. A kilogram is 1,000 grams. Okay? By definition, kilo means 1,000. And so here's just an example of the FDA recommendations for like daily nutrients of different things. And you can see the measurements given for scale, right? So the FDA recommends about 44 grams of protein, which is actually like pretty low, but
Yeah.
right, vitamin C, 60 milligrams. Vitamin B12, 6 micrograms, right? Really tiny amount of vitamin B12. Right, calcium, you need about 1,000 milligrams. Copper, 2 milligrams, right? So this is just given to show scale, right? Different things are given in different scales. All right, fill in the blanks with the correct prefix. 1,000 meters is one what?
Kilometer?
Kilometer, so kilo, K. Kilo is abbreviated with K. All right, 1 times 10 to the negative 3 grams is what? So if you go to your small scale, 1 times 10 to the negative 3 is a milli.
Milligram.
And so milli is abbreviated lowercase m. And 0.01 is what?
Centimeter? Is it centimeters?
Deci. Oh, yeah, sorry, centi, excuse me. Abbreviated with lowercase c. You guys should have these memorized. By the time you're done with the semester, you definitely will have them memorized just from using them, but you may want to commit these to memory. Okay, so there were the answers, right? Centi, milli, kilo. Okay. So lengths are often broken down with centimeter or millimeter for reasonable measurements, right? So ophthalmologists measure an eye's retina in centimeters, or a surgeon might measure the length of a nerve in millimeters, right? Okay. A meter stick is 1 meter, right? You can break that up. So there are 10 decimeters within a meter. There's 100 centimeters or 1,000 millimeters within 1 meter. Volume can be broken up the same way, right? You have 1 liter is 10 deciliters or 1,000 milliliters. Okay. Deciliter is kind of unique to medicine. I don't know why, but in medicine, they often give like blood concentrations in milligrams per deciliter. So if you work in the medical field, you'll see deciliter all the time, but it's not really used much in the other sciences. Not sure why, but. So converting length to volume is interesting with the metric system. So a cubic centimeter. So if you took a cube, right, where the length of one side is a centimeter, the total volume of the cube would be expressed as 1 cubic centimeter, right? Length times width times height. By definition, 1 cubic centimeter is 1 milliliter. And so that's why the metric system is cool, is because your lengths directly convert to volumes, whereas the English system, we use feet and inches, but then we use ounces. And there's like no conversion that makes sense between like feet and inches and ounces. It's just like they're totally different scales. Whereas the metric system, volume and length are directly correlated. Now in medicine, they abbreviate cc for cubic centimeter. I don't know why they do that. It's really annoying. So if you work in a hospital setting, it's always going to be, you know, so many cc's of something. That's the same thing as mils, right? But it's unique to medicine. Okay, and so here's just another example showing you, right? Like a cubic centimeter is a mil. And then if you had 1,000 cubic centimeters, that's a liter. Okay. And so mass, we use grams, right? And so a kilogram is 1,000 grams. You can also have centigrams or milligrams or micrograms. Now, in medicine, they use the abbreviation MCG for micro. Everyone else in the scientific community uses the Greek letter mu, which looks like that. Okay, that stands for micro. Okay, so it looks like a U with an extra long thing in front of it. That's mu, right? So microgram or MCG. So these are interchangeable. Okay, so study check. Identify the larger unit in each of the following. So what's bigger, a millimeter or a centimeter?
Centimeter?
Centimeter.
Centimeter is bigger. Kilogram or centigram?
Kilogram?
Kilogram. A milliliter or a microliter?
A
Milliliter?
milliliter.
Milliliter is bigger. A kiloliter or a microliter?
Kiloliter.
Kiloliter?
Okay, looks like you guys got the concept. All right, there's the answers. All right, so conversion factors are the next thing we're going to talk about. So a conversion factor is converting from one unit to another. Okay. So here are some equalities, right? You have a meter is the same thing as 1,000 millimeters. A pound is 16 ounces. 2.2 pounds is 1 kilogram. These are your equalities, right? 1 meter equals 1,000 millimeters. Okay. Now you can write these as fractions. You can say 1 meter per 1,000 millimeters, or you can write it the other way. You can say 1,000 millimeters per meter, right? So anytime you have an equality like this between two different units, you can write it as a fraction, but you can write the fraction one way or the other. Doesn't matter which way you write it, right? Because there's 1 meter per 1,000 millimeters. There's also 1,000 millimeters per meter. And so here, your book uses example 60 minutes per hour. So you can write that as 60 minutes per 1 hour or 1 hour per 60 minutes, right? You can write the fraction either way. The reason why this is important is because when you start doing math problems, you're going to have to input your conversion factor in there, and you're going to want to put it one way or the other, depending on what you're converting. So we'll do some examples to clarify that. Here are some common equalities. So you don't have to memorize these. You'll probably have a lot of these memorized already, right? Like 1 foot is 12 inches, a yard is 3 feet. You guys pretty much always know that, right? A gallon is 4 quarts, a quart is 4 cups. Maybe you didn't know that a mile is 5,280 feet, right? And then there's conversions between metric and the US system, and these are less commonly known. But like you can look these up online, right? I'm not going to make you memorize these, but 2.54 centimeters is an inch. 1 meter is 39.4 inches. A kilometer is 0.621 miles. Okay. So these are your conversion factors. So let's write a conversion factor for each of these. So how do you go from liters to milliliters?
1 liter is 1,000 milliliters.
Good. Right, and you can write that as a fraction, 1 liter per 1,000 milliliters, or you can write it the other way, 1,000 milliliters per 1 liter. What about meters to inches?
1 meter is 0.025 inches. Oh, no.
A meter is like 3 feet, right? Meter is 39.4 inches. And then you could write that as fractions, right? And what about meters to kilometers?
I do not know.
What does kilo mean?
Kilo, 1,000.
Right. So 1,000 meters is 1 kilometer.
Yes.
Okay. Not too bad.
Not too bad.
Okay. All right. So there we go. 1 kilometer is 1,000 meters. Looks like we got them all right. So the reason why we mention these conversion factors is, what if you want to go convert from one unit to another? Okay. So get to a practice problem. They're still talking about how to write it as fractions one way or the other. Just insert blank slide. Okay, let's converting units. Let's say, how many minutes are in a day? Okay. So what are some conversions that we know? A day is what?
24 hours, which is
24.
What's an
by
hour?
60 minutes.
2 minutes.
Okay. So if we want to figure out how many minutes are in one day,
24 times 60.
one day, and then we're going to do our conversion factor. We know that there's 24 hours per one day. And then we know that there's, sorry, that was supposed to be 60, 60 minutes per 1 hour. Okay. And so days are going to cancel. Hours will cancel. And so we end up with 60 times 24.
1,440.
Yeah. And so this is why we practice writing the equalities as fractions, is because when you do the math, you want them set up as fractions. Okay. Now, your book also talks about percentages, okay? And so percentages are also fractions, but they are using 100 as the base. So if you find out that you're like 18% body fat, the fraction would be you have 18 kilos of fat per 100 kilos of body, right? So it's just a conversion, 18 to 100. So anytime you see a percentage, the conversion is that number to 100 by definition. Right, so if there's a piece of salmon and they tell you the salmon is 1.9% omega-3 fatty acids, what is your equality there?
1.9% of 100.
Yeah, 1.9 grams of omega-3
Divided by 100.
Out of
per 100 grams of salmon. Right. It's just that number per 100. That's all of percentages. All right. Okay. So write the equality and conversion factors for the following: meters and centimeters. What's the equality there? 1 meter is how many
meters,
centimeters?
100.
100.
100.
So if you wanted to write that as fractions, you could write it one way or the other, right?
18% of gold per gram, per 100 grams.
Yeah. 18 grams of gold per 100 grams of jewelry. And 1 gallon of gas is $3.40.
That's better than what we are paying now.
Yeah,
I was waiting for something.
this is probably the accurate price when the book came out, but
Per gallon.
yeah, so it's gonna be $3.40
40 cents per 100 gallon.
For 1 gallon.
Why did I say 100 per gallon?
Yeah. Or you
That's
can
a
write
lot
the
of
other way.
money.
You could write it the other way, right? 1 gallon per 340. All right. So let's skip ahead here. Skip ahead. Okay. So let's do a practice problem. If a person weighs 164 pounds, what is their mass in kilograms?
You said the kilos is 2.20
Mhm.
per pound.
Yeah. So 164
And 2.4.
pounds, and we want to multiply that by our conversion factor. Now, we want to get rid of pounds, so we want the pounds on the bottom. So 2.2 pounds per 1 kilogram. Right? So pounds will cancel. $74.545454 repeating. So what do we want to round this to be accurate?
74.5.
Yeah, the conversion factor is actually 2.20. Let me be accurate here.
Oh,
No.
okay, okay. So
3
it's
sig figs.
74.55.
No, 74.5. 3 sig figs, 3 sig figs, 3 sig figs. Any questions on that one? Okay. So there we are. 1 kilo is 2.2. And so you can write it as a fraction either way. So when you're converting, you want to make sure pounds gets canceled. So you put the kilos on top, pounds on bottom. 74.5. Okay. A rattlesnake is 2.44 meters long. How long is he in centimeters? So 1 meter equals 100 centimeters. So 2.44 meters. What do we want to put on top? Centimeters or meters?
Centimeters.
So 100
Centimeters, so we
centimeters.
want to get rid of it.
Yep. And 1 meter on the bottom. That way the meters cancel. So not too bad. Okay. All right. So in chemistry, a lot of times you have more than one conversion factor. The last 2 examples we did were easy because it was just one conversion. So sometimes you're going to have multiple. So a doctor prescribed a dosage of 0.15 milligrams of Synthroid. The tablet in stock contains 75 micrograms. How many tablets do you need?
2.
Yes. The math is simple on this one, so it's easy to do it in your head, but the way you would do it is with conversion factors. So you're starting with 150 milligrams and you want to go 1,000 micrograms per milligram, and then 1 tablet per 75 micrograms. So milligrams cancel, micrograms cancel, and you end up with 2 tablets. How many minutes are in 1.4 days? It was kind of like the example we did previously. So how would we set this up? So we want to get rid of days. and we want to go to hours. So how many hours in a day?
24.
And then we want to get to minutes, right? So we want minutes on top and we want hours on the bottom. And so there's 60 minutes per 1 hour. So 1.4 times 24 times 60. And you end up with 2 times 10 to the third. If your pace on a treadmill is 65 meters per minute, how many minutes will it take you to go a distance of 7.5 kilometers? So let's start with the known distance.
How many meters are in a kilometer again? Oh, we said 1,000,
Mhm.
right?
So
Okay.
let's
So we're
start
gonna
with-
take 65.
So 7.5 kilometers, because that's how far we want to walk. And we want to convert that to meters.
So
So 1,000 meters per 1 kilometer. And then we want to get to minutes. And our ratio is 65 meters per minute. So for every 1 minute, you go 65 meters. Because that's what was given here. So kilometers will cancel kilometers, minutes will cancel minutes. Oh, sorry, meters will cancel meters, excuse me.
650 minutes.
Is it 650?
I don't know. I just guessed. Let me
Oh.
actually do
I
it. I'm
got,
sorry.
that's what I got in my head.
7.5 times 1,000 divided by 65. So that's your calculator answer, but we want to round it, right?
0.4
To how many sig figs?
to
2?
Right. So how do we round this to 2 sig figs?
Scientific notation.
Or
We could just say 11 point.
not
It's
11.
120.
Maybe 120.
Because of 0. Okay.
All right. So last thing we're going to talk about is density. Okay. So density is basically mass divided by volume. Right. It's the ratio of mass to volume. Okay. And so here's an example of density, right? Different objects of different densities in water. And so things that are more dense than water sink, things that are less dense than water float. Okay. And so here are some densities of common substances, right? So wood, maple wood is like 0.75 grams per milliliter. By definition, water is 1 gram per milliliter, right? So anything higher than 1 is more dense than water. Anything less than 1 is less dense. So like olive oil is 0.92. That's why oil floats on top of water. Some of the most dense things are metals. So you can see gold is 19.3 grams per mil. So actually like a brick of gold is like one of the heaviest objects. It's like they're really heavy. Lead is only 11.3. Yeah.
Professor, you said water is 1 gram per ml.
Yeah.
Is that correct? Okay, thank you.
Yeah. So the reason why water is exactly 1 is they used water as the basis for the metric system. And so the unit of mass in the metric system is the gram, right? they came up with that because they wanted a system that easily converted volume to mass. So they said, let's measure 1 milliliter of water, and whatever that weighs, we're going to call that a gram. And so the metric system is based on water, right? Even temperature, right? Like 0 degrees Celsius is the freezing point of water. Water is the most abundant thing on Earth, pretty much. And so they based the whole system on water. So it's kind of cool. But anyway. Okay, so once again, density is the mass of a substance divided by the volume of the substance, right? How much it weighs divided by how much space it takes up. It's usually given in grams per milliliter. Sometimes, like for gases, they're given in grams per liter. It just depends, but it's always a mass divided by a volume. So how do you measure volume of an object? This is kind of a simple question, but it can be tricky, right? Like how much volume does your body take up? How would you
Like
measure
the
that?
amount of space it takes up?
Yeah, how do you measure the amount of space something takes up?
The measurement, like for instance, like a human being, the circumference of like,
Right, it would be kind of hard. You'd have to take a bunch of measurements, right? So the quick and simple way is you dunk something in water and see how much the water level rises. So that is like a quick, ingenious way to measure the volume of something. So if you have a
how
graduated,
interesting.
if you have a graduated cylinder with 25 mils of water and you drop this little object in there and the water goes up to 33 mils, how much does the object, or how much space does it take up? The 8 mils, right? And so that's actually how we measure the volume of things, is we just dunk them in tanks of water and see how much the water goes up, because that's the quickest and easiest way. Actually
So
have
this-
really big tanks that like can fit people. So if you want to get a really accurate measurement of like what your body fat is, they'll actually submerge you in water and see how much space you take up, and then they'll weigh you and do these weird calculations.
Oh, wow, that's interesting and sad, but like know what to submerge, like the amount of weight to come up with the volume.
This is just a measure of volume, right? This little object can weigh whatever, but the volume is the displacement of water. To weigh it, you just stick it on a scale.
So it's basically whatever you're trying to figure out the amount of.
Yeah. This is just a quick method for figuring out how much space something takes up. So, what is the density of a 48-gram sample of metal if the level of water in the cylinder rose from 25 to 33 mils after the metal was added? So the volume displacement in this example is how many mils?
8 mils.
8 mils. So 8 mils, and let's say the mass was 48 grams. So what's the density?
6.
Right. So that's how you calculate density. It's just the mass divided by the volume. Okay. Skip the part about calculators. Okay, here's a word problem. So John took 2 teaspoons of cough syrup. If the syrup has a density of 1.2 grams per milliliter, and there's 5 milliliters in 1 teaspoon, what was the mass in grams of the cough syrup?
60.
No.
Oh, because I didn't divide. Yes.
So here's how we'd set it up. We're starting with teaspoons. And then our next conversion factor is to go from teaspoons to milliliters. Okay. And then our next conversion is to go from milliliters to grams. Okay. So 2 teaspoons times 5 mils per teaspoon times 1.2 grams per mil gives you 12 grams.
I only took the 5 milliliters and multiplied it by 12 grams, which it's not even 12 grams. So I don't know. Why I did that.
1.2. Do you guys have any questions on how to set these up? I know we're like almost out of time, but
So you take what you want to figure out or what the given is, which is the 2 teaspoons. And then you take the conversion factors of what you know.
mhm,
Okay.
to get to what you're curious about.
got
So
it, okay.
they're telling you you have 2 teaspoons. That's your start. And they're asking you for grams of cough syrup, and that's the finish. So you want to start with teaspoons and get to grams of syrup. And the way you get there is with the conversion factors. All right, the last thing we're going to talk about in this chapter is specific gravity. If any of you guys do like home beer brewing, you're probably familiar with this term. Specific gravity is just a ratio of the density of your sample divided by the density of water. Most scientists don't use the term specific gravity, but it's used in industry and in medicine a lot. And so it's a ratio of how dense a liquid is compared to water, right? And so specific gravity is usually used for liquids. And so like if you're home brewing beer, you measure the density of your beer versus the density of water, and that's the specific gravity of your beer. And beer with more alcohol is less dense because alcohol is less dense. So like a beer with a lower specific gravity is usually like higher alcohol percentage. That's actually how they calculate the alcohol percentage in beer or wine. Is
Interesting.
the change in density. It's just like a quick, easy way to do it. So you can just measure the density of your liquid, and then that's how you, yeah. So an unknown liquid has a density of 1.32. What is the volume of a 14-gram sample of liquid?
So it would be 1.32 times, or 1.32 over the density of water. I don't know where I'm going with this. I'm going to just stop talking.
So a liquid has a density of 1.32 grams per mil. What's the volume of this much sample? So 14.7 grams of liquid, and our conversion factor is this. And so we want to get rid of grams, 1.32 grams per 1 milliliter. And so 14.7 grams are going to cancel, divided by 1.32. And that's 11.13636636 repeating forever. And so what do we want to round this to? How many sig figs?
3,
3 sig figs. So
Three.
what's our final answer?
11.1.
11.1 milliliters. Don't forget units. Okay. So 11.1 mils of liquid. All right, so that concludes chapter 2, and looks like we're right on time, so that was perfect. So once again, we talked about measurements, metric units, SI units, measured numbers versus counted numbers, right? Prefixes, right? Milli, kilo, things like that. Right? Talked about density, significant figures, rounding, right? So, all right. If you guys have any questions, feel free to shoot me an email.
Is there a class on Monday by any chance?
There is no class on Monday. Monday is a holiday.
Oh, thank you for asking that, because I would have shown up.
Yeah, I believe is it Labor Day?
Yes.